This presentation covers the Xcite 1200T-9 system setup and operation. The Xcite 1200T-9 is manufactured by Xcite Systems Corporation in Cincinnati, Ohio. It is a torsional exciter capable of applying an inertial torque while rotating at speeds up to 4,000 RPM. This torque generation is accomplished by a closed-loop system which oscillates an inertial disk at frequencies independent of the rotational speed. This presentation is broken into 6 parts. The first is system components. Second, theory of operation. Third, system setup. Fourth, system operation. Fifth, system shutdown. And sixth, system troubleshooting. The ES315 exciter head is a continuous rotational torsional exciter consisting of a limited rotation hydraulic actuator whose body is attached to a mounting flange which is mounted to a structure under test. Alignment of this mounting flange with the turbine rotor is critical and is discussed later in detail. The rotor of the hydraulic unit is attached to an inertial disc which has 6 clearance slots for the mounting flange standoffs. The radial acceleration of this inertial disc creates the inertial torque which is imparted to the rotating structure. The relative position of the hydraulic body and the rotor are measured via magnetic pickups. The time delay as 2 tick pins pass the 2 magnetic pickups is measured and converted to a 0 to 25 degree rotation by the master controller. The 2 magnetic pickups are held by a bracket which allows the spacing of the pickups to be precisely set to the tick pins, and this gap alignment will be covered later in the presentation. The master controller is a closed-loop servo controller which allows independent control of the static position of the inertial disc and the peak dynamic torque generated during its oscillation. The functions of this controller are explained later in this presentation. The 1201B DP hydraulic power supply is a 5 gallon per minute hydraulic unit with 2 pressure ports. The first is a 3000 psi pilot stage pressure for the servo valve, and the second is a 1000 psi working pressure for the hydraulic actuator. Theory of operation. The components are connected such that a reference oscillator provides a drive signal to the master controller. The master controller then sends a signal to the servo valve of the actuator, causing the inertial disc to oscillate. The angular position of the inertial disc with respect to the body of the actuator is fed back via magnetic pickups to the static loop of the servo controller. Dual pressure transducers across the vanes of the actuator then measure the differential pressure and therefore the dynamic torque of the system, and that is fed back for control to the master controller. All controls for the operation of the system during operation are done at the master controller. This video demonstrates the operation of the exciter head when a low frequency signal is applied to the master controller, causing the motion of the inertial disc with respect to the body of the actuator. The system is spinning at 3000 RPM, and yet there is independent control of the frequency of oscillation of the disc. The servo valve and manifold are stationary while the exciter is rotating, and the relative positions of the body of the actuator and the inertial disc are constantly monitored by magnetic pickups. The exciter is mounted to the turbine rotor with the mounting flange, which is connected to the body of the actuator via 6 standoffs. This rigid connection then makes the body of the exciter one continuous structure with the mounting flange and therefore the turbine rotor. The rotor of the hydraulic actuator is connected to an inertial disc, which can oscillate with respect to the body of the actuator. The relative position of the body of the actuator and the inertial disc are constantly monitored by magnetic pickups detecting the passage of 2 tick pins past their faces. There is a hydraulic rotor coupling which is stationary and imparts the oil pressure in return to the rotating exciter and back to the hydraulic power supply. The differential pressure across the vanes of the actuator is controlled by a servo valve which is driven from the master controller, and 2 pressure transducers feed back the differential pressure across the vanes of the actuator, which then provides a measurement of the inertial torque. This shows a cross-section of the hydraulic actuator and the rotor, which has differential pressure applied across its vanes. The angular acceleration of the rotor created by the differential pressure then is multiplied by the inertia of the large disc, which creates the dynamic torque, which is then imparted to the structure under test. The peak dynamic torque of the system is shown, where being an inertial system at low frequencies, the acceleration is lower and only increases as with the increase of frequency. Therefore, the torque increases to the maximum capability of the system at roughly 40 Hertz. This peak amplitude of around 4,000 inch-pounds is then held across a broad frequency range, and it will then decline at the upper frequencies. The exact performance of the system will be dependent upon the exact dynamics of the turbine rotor under test. System setup. The exciter is mounted to the turbine rotor via a mounting flange which has 6 clearance holes for mounting bolts and 3 set screws which are used for alignment of the face of the flange to the face of the turbine rotor, and for extraction of the flange when the system is being dismounted. To mount the exciter, lower the unit to the corresponding mounting flange on the turbine rotor and insert the 6 mounting bolts. The alignment of the exciter to the turbine rotor is measured with a dial indicator measuring the smooth surface at the end of the actuator. It is very important that the alignment be achieved within 1 mil, 0.001 inches, peak to peak at this point on the exciter. This will guarantee a vibration level which will be safe for the operation of the unit. The alignment is accomplished while slowly rotating the rotor, therefore the body of the actuator, measuring its runout, and by trial and error adjusting the 3 alignment set screws to bring the alignment within the 1 mil specification. The 2 magnetic pickups must be adjusted such that the gap between the face of the pickup and the face of the tick pin is no more than 0.1 inches. A gap greater than that will not allow a sufficient signal to be fed back to the controller to measure the angular position. When mounting the magnetic pickups, it is critical that the colored dot be in the direction of rotation of the discs. Otherwise, there will not be enough signal to trigger the flip-flop in the master controller. Once the exciter head is mounted and aligned, the cables need to be connected. The reference oscillator is connected to J308, the program input of the master controller. J307 is the power connection control to the 1201B dual pressure power supply. The interlock plug J308 must be inserted and connected. The J305 head cable connects to the servo valve and to the 2 pressure transducers. There is no polarity required for the pressure transducers since they are measuring the differential pressure. So it does not matter which cable connects to which transducer. The J311 displacement cable is connected to the 2 magnetic pickups, and these are very, very important for their polarity and are discussed in a subsequent slide. The J309 pigtail from the J311 displacement cable is then connected to the J309 external static input. When determining the connection to the 2 magnetic pickups, one must first determine the rotation of the rotor under test. And the rotation convention for the ES315 exciters is defined as clockwise when viewing the rotation of the inertial disc from the servo valve end of the exciter. Counterclockwise is the opposite direction when viewing from the servo valve end of the exciter. When connecting the cables, never switch the B and C cables going to P1 and P2. The connectors which plug into the magnetic pickups are wired differently and must be reversed at the magnetic pickup when changing from counterclockwise to clockwise rotation, as shown in the previous slide. The cables are now ready to be connected, and the servo valve cables connected, along with the two pressure transducers. There again is no polarity concern for these transducers since they are measuring differential pressure. The two magnetic pickup cables are now connected, paying very close attention to the instructions on the page SN09 of the instruction manual regarding which magnetic pickup is connected for P1 or P2 based upon the rotation of the rotor. The three hydraulic hoses, the two pressure and the one return hose, are now connected. They are polarized, so they cannot be connected incorrectly. The system is ready now for connection of the cables. The reference oscillator is connected to J308, the program input. J307 power is connected to the hydraulic power supply. The interlock plug J306 must be connected, and the head cable is connected to J305. The displacement tick pin magnetic pickup cables are connected to J311 displacement, and its jumper B and C is connected to J308, the external static input. The cables are now connected to the master controller, starting with the power cable, the interlock plug, the exciter cable to the servo valve and pressure transducers, the output from the oscillator to the program input, setting the static input to external so that it reads the displacement being fed from the displacement cable J311, which is monitoring the output of the magnetic pickups. Using an oscilloscope, you can then monitor the angular position of the two discs, and for troubleshooting you can monitor the width of the pulse created by the two magnetic pickups. This will be demonstrated later. The torque is measured from the load cell output of the master controller. The three hoses are now connected to the 1201B dual pressure hydraulic power supply. There are 2 pressure and 1 return quick disconnects, and all 3 are polarized and sized such that they cannot be connected incorrectly. The power cable is now connected to the controller input on the hydraulic power supply. When setting the switches on the master controller, it is extremely important to follow the directions under System Operating Procedure, paragraph 4 of Setup and Operation of the manual. This is on page S&O 10. Failure to set the switches on the front of the controller will cause improper operation of the exciter. In similar fashion, all switches on the back of the master controller must be set precisely the way the manual dictates in Section 4, Operation Procedure. It is critical that all switches be set in the position which is shown in the manual. The hydraulic power supply is now turned on, and verify that you are reading 1000 psi and 3000 psi on the 2 pressure gauges. First, the power to the controller is turned on and the pump is started. You can test the high temperature, low temperature, and filter restriction monitors by pressing the lights and watching them illuminate. The high pressure gauge should be reading 3000 psi. This is the pilot stage for the servo valve. The low pressure gauge should be reading 1000 psi, which is the working pressure for the actuator. Once the hydraulic power supply is started, the system under test can be rotated. It is very important to protect the hydraulic actuator and the rotary coupling, that there be hydraulic power to the exciter whenever it is rotating. When the rotor speed reaches approximately 400 RPM, the static signal meter will move to its 50% full scale position. This indicates that the control loop is locked on and that the inertial disc position is being maintained in mid-stroke. You now move to static and then to static plus dynamic. Once the rotor is spinning and until it gets up to about 350 RPM, the static needle will stay below 0. Once the speed has reached the 350 RPM level of speed, the static loop will lock on and the system can then be moved to static and then static plus dynamic. This shows now the dynamic torque being generated into the turbine rotor. Once the test is complete, the standby knob is moved back to static and then to standby. Shutdown procedure. Once the test is complete, the turbine rotor can be shut down. It is very important that the hydraulic power supply be left on until the rotor completely stops turning. This video shows the procedure of moving from static plus dynamic to static to standby, then shutting down the rotor under test. Keep in mind the hydraulic power supply must still be running while this shutdown takes place. Once the rotor has completely stopped, it is then safe to shut down the hydraulic power supply. Dismounting the exciter. Once the test is complete, the 6 mounting bolts are removed and the 3 set screws are used to extract the mounting flange from its mate on the end of the turbine rotor. To remove the exciter, first connect the overhead crane and then remove the 6 mounting bolts. After they have been removed, use an Allen wrench and slowly use the 3 set screws to extract the exciter from its mating flange on the turbine rotor. System troubleshooting. The 2 main things to check if there are any problems with the system are, number 1, the hoses and servo valve cables. These are shown in the following video. To check the connection of the hydraulic hoses and servo valve cable, move the tension compression switch back and forth while watching the inertial disc. It should be moving from one end of its stroke to the other as the drive to the servo valve is reversed. This indicates that all hoses are connected correctly and that the cables are connected correctly. At the end of your checking, be sure to leave the switch in the compression counterclockwise position. If the mass does not center when the rotor is above the 300 to 400 RPM range, then you need to check the magnetic pickup cables and the square wave output. This is shown in the following video. As a diagnostic tool, the output of the flip-flop, which is fired by the magnetic pickups, is available on the back of the master controller. When the static position is changed and the angular position between the mass and the actuator changes, the width of that pulse will be changing. If there is no pulse shown, then there is a problem with the output of the magnetic pickups. When there is proper operation, as you change the position of the static set point, you will see the width of that pole, that square wave, change. If you do not get that square wave, then you need to check the output of the magnetic pickups. This is done by inserting B and C T's at the P1 and P2 cables at the J311 connector. The output of the two magnetic pickups must be at least 5 volts to fire the flip-flop. If you are not getting at least 5 volts by about 400 RPM, then recheck the gap of the pickups. This video is showing P1 and P2 and the time delay between them during proper operation. This concludes the troubleshooting section for the presentation. Please read and follow all of the instructions which are contained in the system's operation manual.